So your handout describes a process, an experiment. It's basically dissolving a ionic substance in water. That ionic substance is potassium nitrate. Okay. So we talked about this morning. Remember what equilibrium expression looks like, right? So if we dissolve this in water, it starts out as potassium nitrate solid. And when it goes into water, it dissolves and forms the potassium plus ion and the nitrate anion. Okay. So basically, whatever the starting concentration, because it's a complete ionization, it completely dissociates into its ions. So whatever the concentration of the starting material, which is our potassium nitrate, is, then that is what the concentration of each of the ions will be. So basically what we have to do is calculate that concentration over a range of volumes. Okay, so the experiment was initially to take some of that solid, dissolve it in water. We were going to take 20 grams of it. We were going to dissolve it. We were going to add what's on our sheet here, 20 grams, and we're going to add 15 milliliters of water. After we add the 15 milliliters of water, we were going to read the final volume. Okay, that was going to be hot water. So then we're going to start letting the tube cool down. That was going to be a clear solution. Okay, so we were going to start letting the tube cool down until we started to see the first little trace of formation of solid back in the tube again. Okay, so at that temperature, we will record it. We record the temperature at that moment when we start to see crystals form for the first time. Okay, so you got your initial volume and your initial temperature. So that's all the data that you would have been collecting yesterday. Okay, so what that told you is that when you first saw the first little formation of white crystals, that tells you that that is where the temperature, where the equilibrium exists between solid potassium nitrate and the dissolved form of potassium nitrate, which is the potassium ions and the nitrate ions. Okay, so at that point where you start to see the crystals, that's when this equilibrium occurs. So basically, you would have been determining the point of equilibrium for this system, the volume and the temperature. Okay, actually, the temperature. You were going to be determining the temperature because your volume is something that you were going to be able to measure directly. Okay, so that will be for the first one. So the data I gave you gives us, for V1 and T1, it gives us 23.9 milliliters as being the initial volume, 17.5 degrees Celsius as being the temperature at which those crystals started to appear. Okay. So then the next thing we were going to do is to do it again. We're going to add some more water and see what effect that has on the equilibrium position. So when we add more water, that changes the concentration, right? Same tube, just adding more water. So now we're going to cool it down again until the little white crystals appear. That takes place at a different temperature this time. So our volume reading for the data that I gave to you is 29.9 milliliters, and the temperature is 55.2. Okay, you see where I'm going? So every time after you take the temperature, you're going to add more water, let it heat up and cool down again to see what temperature that the crystal started to appear. For each one of these systems, you are in essence determining the equilibrium position based on measuring its temperature and volume. Right. So we did this for a bunch of them because that's what we needed to do in order to use our Excel tools to be able to determine enthalpy. This will all make sense once we actually start doing the calculations. So dissolve the solid. It was soluble in solution. Found the temperature at which it was. So that's where we get this equilibrium from. So in each case, we can calculate the starting concentration of potassium nitrate, right? Because the paper told you that you're weighing out 20 grams and you measure the volume in each case, right? So in each case, the number of moles is going to remain the same. 20 grams of potassium nitrate divided by or multiplied by 1 over the molar mass is 100, which is 139 grams per mole. And that gives us, even put that in there, 0.1439 moles of potassium nitrate. So that's constant, right? It stays the same. That amount of potassium nitrate has been added to the tube and it never changes. We just keep adding the liquid to the top, more volume, more water, but the amount of moles of potassium nitrate does not change. Okay? All right, so now that we know how many moles that we have, what is molarity? Moles over liters. So now that we know the number of moles of potassium nitrate, we can calculate the concentration in each case. So try to go down just a little bit. Okay. So for this first one, it would be molarity would be 0.1439 moles over the liters, the volume in liters, which is what? Right. 0.0239 liters. So that gives you the concentration of the trial one. For the second one, you have 0.1439 moles again. And this time the volume is different. So the only thing that's going to change is that we're going to keep changing the volume in each case. And in those steps you can calculate the concentration of each of those solutions. So from the data that you have in this trial sheet right here, that's what the first thing for us to do is going to be. I'll continue to bring a marker. So the first thing that we need to do is calculate concentration. So we're going to set up a table in our Excel that's going to, I'm going to show you how to plug the formulas in to calculate the concentration using moles over liters for the data that we have entered in this table form. Okay. The next thing that we have to do is, so that's where we get our concentration from for each one of the samples. The next thing we have to do is calculate our delta H value. Remember what I told you this morning? So all the parameters that we want to calculate are delta T, delta H, and delta F. For all of these things we talked about this morning, in order to calculate the Gibbs energy, we need the equilibrium constant, right? Let's just remember what all these equations are. Delta G is equal to negative RT natural log of K. Delta G is also equal to delta H minus T delta S. Okay, delta H we're going to have to find graphically, but for right now we know that it's equal to delta U plus P delta V. We don't have any of those variables, so we're not going to be able to use this one. We're going to have to go about it a slightly different way. For K, it's just K. But we also know that we can calculate K for any reaction that has reactants going to products to be the product of the products raised to the power of their stoichiometric coefficients over the reactants raised to the power of their stoichiometric coefficients. And we know that for any substance that is not aqueous, we don't count it in the equilibrium constant expression, right? And delta S we can get from the delta G equation. So the best thing for us to do right now, the most helpful thing for us to do is going to be to first calculate K. Put this in order. Okay, so for each one of these, we're going to do this for each one. And I'm going to show you how to do it in Excel. I'm sorry, this thing just jumps and it gets on my nerves so bad. All right, we're going to calculate K first. So let's just do it for trial one. I'm just going to do all of these parameters for trial one. You want it closer to the screen? Oh, you want me to go back and, okay. Yeah, okay. There is no little bit with this thing. Okay. That's, okay. Okay. All right. So the first thing we do is calculate K. K then is going to be the concentration for trial one, which is what? Well, remember we said that if the concentration of potassium nitrate is what? What is the concentration that we calculate for potassium nitrate? From trial one. The number of moles, okay? 6.2 molar. Okay. So we know that since it completely dissociates in aqueous solution, that the concentration of the potassium nitrate is equal to the concentration of the potassium, which is also the same thing as the nitrate. It's all the same, right? Oh, okay, thanks. All right. So therefore, when we set up the equilibrium expression, we have potassium ion times the nitrate ion, and there is no denominator, right? Because that's a solid. Potassium, solid. So K for this one, that is the concentration of the solution for the first trial. So the moles of potassium nitrate over the volume for trial. 6.02. Does everyone agree with that answer? 6.02 moles per liter or 6.02 molar. Okay. Okay. All right. So therefore, in order to get the value of the equilibrium constant, in the equation that we saw earlier, the equilibrium expression, the reaction, there are no stoichiometric coefficients. The coefficient is 1 in each case. So therefore, 6.02 is going to be raised to the power of 1. It's also going to be 6.02 here. And then what is the value that we get when we multiply those two? And basically, this is the same thing as the KNO3 concentration squared, right? What do you see it here? Oh, up here? Oh, I was just showing you the reaction. Uh-oh. Mm-mm. No, not at all. I'll move it over because I can't move the projector. Move it over just a little bit. This is the equilibrium reaction. Okay, so I had written it earlier at the very beginning, but I just rewrote it right here to give us a chance to remind ourselves that there are no coefficients. So it's just solid potassium nitrate and with the potassium ion increase and the nitrate ion increase. So what we know about this dissociation is that whatever this concentration is of potassium nitrate, the concentration of potassium ion and nitrate ion is the same, which is where I got this from. Well, kind of, sort of, but let me make sure that we're on the same page. So because of this right here, Medium highlighter. Okay, so because potassium nitrate concentration is equal to the potassium ion concentration, and it's also equal to the nitrate ion concentration, they're all equal. So when you have in your equilibrium constant expression that potassium ion times nitrate ion concentrations, right, it's the same thing. It's just saying, um, here's my same thing as just saying KNO3 squared. Okay. All right. So let me hurry up and finish with the theory so we can get to the Excel. All right. So that's how we get the equilibrium constant each time. What answer did we get? Okay. All right. So that's our equilibrium constant. So we got that. So now we need to calculate our enthalpy. And the way that we do that is by graphing our equilibrium constant versus our temperature. The way that we know how to do that is delta G is equal to delta H minus T delta S. Delta G is also equal to negative RT. I told you PChem was a lot of math. Natural log RT, natural log of K. So the fact that both of these things are equivalent, we can set these equal to each other. Delta H minus T, let me put this one first, minus RT natural log of K is equal to delta H minus T delta S. Because they both equal to delta G, we can set them equal to each other. All right. So therefore, if we want to get natural log of K by itself, we need to divide both sides by negative RT. So when we do that, this is what we end up with. Does everybody see that? So we divide both sides by RT, and we did so delta H divided by RT plus, because we divided the temperature is canceled here. See? So T delta S divided by negative T delta S divided by negative RT, the T is canceled, and so it just leaves with a positive delta S over R. What delta be doing? Oh yeah, we need that. That's important. Okay. Okay. So everybody sees where all that comes from. And so now we remember, oh God, this thing kills me. We remember our equation for the line, for a line that we talked about in the last Excel tutorial. So if we rewrite this, it's the same thing. I wish I could. Can I go down? Can I just go all the way down? Okay. Let me just erase this from right here and go all the way down. Start. All right. We go to the next page. And guess what? It didn't want to jump away this time. Okay. Natural log of k is equal to negative delta h divided by r times 1 by t. Right? Same thing, right? Okay. Plus delta s over r. So this is in the form of the equation of a line. So wherever the intercept of this line is going to be the value of delta s over r. Whatever the slope of this line is, it's going to be equal to delta h over r. Okay. So basically what we want to do is, using this template for the equation of the line, we would then plot the natural log of k on the y-axis. We would plot 1 divided by t, which is our x value here, on the x-axis. And then whatever number we get, be it positive or negative, will be our slope, which is the same thing, which is equal to negative h divided by r. Uh-oh, let me move this over. Here, do that. Okay, so delta h divided by r is equal to the slope. So imagine how we're going to calculate delta h. We're going to multiply the slope of that line by r. And r is the constant, 8.314. So to calculate delta h, we're going to say r times the slope. We're just going to rearrange that equation. Okay? No. Oh, it would be, the negative h would be equal to that. So if you want to just find the delta h, it's going to be, thank you, the negative of this product. All right, so that's enough of that. So that's how we're going to get all these parameters. So let's go back and make sure that we know how to get everything. We know we got the K already by using the concentration for each trial. We can find delta H by plotting the values that we get for each trial, because delta H is one of those things that does not change from trial to trial. Okay, so therefore it's going to be the same for all of these trials, delta H. So therefore we can use the delta H that we calculate from this slope now to plug back in to get our delta G, our delta S. Okay, so let's just give it a shot. Y'all ready? Good. All right. So